Ground fault interrupters, or GFIs, function by continuously monitoring the current flowing in the neutral wire and comparing it to the current in the hot wires. If the GFI detects a difference between these currents, this indicates a ground fault, and the GFI will trip, interrupting the power flow to protect against potential hazards. In a three-phase system, the neutral wire serves a specific purpose. It carries the unbalanced current resulting from the three phases. This imbalanced current is the difference in current between the phases if they are not perfectly balanced due to varying loads on each phase. If a GFI is installed on a circuit that shares a neutral with other three-phase circuits, the GFI may experience nuisance tripping. This means that the GFI trips even when there is no actual ground fault present on the circuit it is intended to protect. The reason for this nuisance tripping lies in the unbalanced current flowing through the shared neutral. The GFI interprets this unbalanced current as a potential ground fault, leading to the unnecessary interruption of power. To ensure the proper operation and maintain safety in a three-phase system that utilizes GFI protection, a critical requirement is to provide a dedicated neutral wire for each GFI circuit. This means that each circuit protected by a GFI should have its own individual neutral wire that is not shared with any other circuits. This practice prevents any potential interference or false tripping that can occur due to imbalanced neutral currents originating from other circuits within the system. By isolating the neutral currents in this way, the GFI can accurately monitor the current balance within its designated circuit and respond appropriately only when a genuine ground fault condition exists. Here is a more in-depth explanation of why dedicated neutrals are important. Firstly, understanding unbalanced current is crucial. In a balanced three-phase system, the currents in each of the three phases are equal in magnitude and are 120 electrical degrees apart. In such an ideal scenario, the neutral current would be zero. However, in real-world applications, it is rare to have perfectly balanced loads across all three phases. Different equipment and appliances connected to each phase draw varying amounts of current, resulting in an imbalance. This imbalance causes current to flow through the neutral wire, providing a return path for the difference in current between the phases. Secondly, GFI are designed to detect ground faults, not imbalances. A ground fault occurs when current leaks from a hot wire to ground, providing an unintended path for current to flow. GFI are highly sensitive devices designed to detect even small ground fault currents, typically in the range of 5 milliamps. When a GFI detects a current imbalance exceeding this threshold, it trips, interrupting the circuit to prevent electrical shock hazards. Thirdly, shared neutrals introduce extraneous currents. When multiple circuits share a neutral, the neutral wire carries the vector sum of the unbalanced currents from all the circuits. This means that the neutral current can be significantly higher than the unbalanced current of any single circuit. The GFI on one circuit will see the combined neutral current, which may include unbalanced currents from other circuits that are not related to any ground fault on a protected circuit. Fourthly, nuisance tripping compromises safety. Nuisance tripping can be a significant problem, as it interrupts power unnecessarily and can disrupt critical operations. More importantly, it can lead to a loss of confidence in the GFI protection, potentially causing people to bypass or disable the GFI, which defeats the purpose of having ground fault protection in the first place. Fifthly, dedicated neutrals ensure accurate GFI operation. By providing a dedicated neutral for each GFI protected circuit, the GFI only monitors the current balance within that specific circuit. This eliminates the influence of unbalanced currents from other circuits, ensuring that the GFI trips only when a genuine ground fault occurs on the protected circuit. This accurate operation enhances safety and prevents unnecessary interruptions. Sixthly, code compliance requires dedicated neutrals in many cases. Electrical codes, such as the National Electrical Code, often mandate the use of dedicated neutrals for GFI protected circuits, particularly in specific applications such as bathrooms, kitchens, and outdoor areas. These requirements are in place to ensure the reliable operation of GFI and to minimize the risk of electrical shock hazards. Seventhly, troubleshooting shared neutral problems can be difficult. When nuisance tripping occurs on a circuit with a shared neutral, it can be challenging to identify the source of the problem. The electrician must investigate all the circuits sharing the neutral to determine which circuit is contributing the excessive unbalanced current. This process can be time-consuming and may require specialized equipment. 8. Dedicated neutrals simplify troubleshooting. With dedicated neutrals, troubleshooting becomes much simpler. If a GFI trips, the electrician only needs to investigate the circuit protected by that GFI, eliminating the need to trace through multiple circuits. This saves time and effort and allows for a quicker resolution of the problem. 9. Consider alternatives for shared neutrals. In some situations, it may be tempting to use shared neutrals to save on wiring costs. However, the potential problems associated with shared neutrals and GFI outweigh any cost savings. Alternative wiring methods such as running separate neutral conductors or using multi-wire branch circuits with dedicated neutrals should be considered to ensure proper GFI operation. 10. Proper installation practices are essential. Even with dedicated neutrals, it is crucial to follow proper installation practices to ensure the reliable operation of GFI. This includes making sure that all connections are tight and secure, using the correct wire size and type, and properly grounding all equipment. By adhering to these practices, the risk of ground faults and nuisance tripping can be minimized. The NEC addresses multi-wire branch circuits in Article 210.4. A multi-wire branch circuit, according to the NEC, consists of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, and which is connected to the neutral or grounded conductor of the system. Multi-wire branch circuits are permitted under specific conditions outlined in the NEC. These conditions primarily relate to ensuring that the neutral conductor is not overloaded and that the continuity of the neutral conductor is maintained. The NEC requires that the neutral conductor in a multi-wire branch circuit be sized to carry the maximum unbalanced load. This means that the neutral conductor must be large enough to handle the current that would flow if all the loads on one phase were energized while the loads on the other phases were energized. The NEC also prohibits the use of a single neutral conductor for more than two circuits. This is to prevent overloading the neutral conductor and to minimize the risk of voltage drop. The NEC requires that the continuity of the neutral conductor be maintained. This means that the neutral conductor must not be broken or interrupted at any point in the circuit. This is to ensure that there is always a return path for current to flow and to prevent voltage imbalances. The NEC also addresses the use of GFI in multi-wire branch circuits. The NEC requires that all 120 volts, 15 amps and 20 amps receptacle outlets installed in dwelling units be GFI protected. This includes receptacle outlets in bathrooms, kitchens, garages, and outdoor areas. The NEC also requires that GFI protection be provided for certain other types of equipment, such as dishwashers, washing machines, and electric water heaters. When using GFI in multi-wire branch circuits, it is important to ensure that the GFI is properly rated for the voltage and current of the circuit. It is also important to ensure that the GFI is installed in a location where it is readily accessible for testing and maintenance. In summary, dedicated neutrals are essential for ensuring the proper operation and safety of GFI in three-phase systems. Sharing neutrals can lead to nuisance tripping, compromise safety, and make troubleshooting difficult. By providing a dedicated neutral for each GFI protected circuit, the GFI can accurately monitor the current balance within that circuit and respond appropriately only when a genuine ground fault condition exists. The electrical codes often mandate the use of dedicated neutrals for GFI protected circuits, and it is crucial to follow proper installation practices to minimize the risk of ground faults and nuisance tripping. When dealing with three-phase systems and GFI, it's also important to consider harmonic currents. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz. These currents can be generated by nonlinear loads such as electronic devices, fluorescent lighting, and variable frequency drives. Harmonic currents can cause several problems in electrical systems, including increased neutral current, overheating of transformers and conductors, and distortion of voltage waveforms. In three-phase systems, harmonic currents can be particularly problematic because they can add up in the neutral conductor. Certain triplet harmonics, which are odd multiples of the third harmonic 180 Hz, are additive in the neutral conductor. This means that the neutral current can be significantly higher than the phase currents, even in a balanced system. When GFI are used in systems with harmonic currents, they can be more prone to nuisance tripping. The harmonic currents can create imbalances in the current flow, which the GFI may interpret as a ground fault. To mitigate the effects of harmonic currents on GFI, several strategies can be employed. Firstly, using harmonic filters can reduce the amount of harmonic current generated by nonlinear loads. Harmonic filters are designed to block or divert harmonic currents, preventing them from propagating through the electrical system. Secondly, oversizing the neutral conductor can reduce the voltage drop and heating caused by harmonic currents. A larger neutral conductor will have a lower impedance, which will reduce the voltage drop and heat generated by the harmonic currents. Thirdly, using a dedicated neutral for each GFI protected circuit, as discussed earlier, will prevent harmonic currents from other circuits from interfering with the GFI operation. Fourthly, using GFI that are specifically designed to be immune to harmonic currents is possible. Some GFI are designed with filters or other circuitry that minimizes their sensitivity to harmonic currents. Additionally, when installing GFI in three-phase systems, it is important to follow the manufacturer's instructions carefully. The instructions will provide guidance on proper wiring and grounding techniques, as well as any specific considerations for three-phase applications. Finally, regular testing and maintenance of GFI is crucial to ensure their proper operation. GFI should be tested monthly to verify that they are tripping correctly. If a GFI fails to trip during testing, it should be replaced immediately. Furthermore, it is important to keep the area around GFI clean and free of debris. Dust, dirt, and moisture can interfere with the GFI operation and may lead to nuisance tripping or failure. Considering voltage imbalance is also important. Voltage imbalance in a three-phase system refers to a condition where the voltages in the three phases are not equal in magnitude or are not 120 electrical degrees apart. Voltage imbalance can be caused by several factors, including unequal loading on the phases, faulty transformers, and imbalanced source impedances. Voltage imbalance can have several negative effects on electrical equipment, including increased motor heating, reduced motor efficiency, and shortened motor life. In addition, voltage imbalance can also cause nuisance tripping of GFI. When voltage is imbalanced, the currents in the three phases will also be imbalanced. This current imbalance can create a neutral current, even if the loads are perfectly balanced. The neutral current can then cause the GFI to trip, even if there is no ground fault. To mitigate the effects of voltage imbalance on GFI, several steps can be taken. Firstly, balancing the loads on the three phases is important. This can be achieved by distributing the loads evenly across the phases, ensuring that each phase is carrying a similar amount of current. Secondly, correcting any faulty transformers is crucial. Faulty transformers can cause voltage imbalance and should be repaired or replaced as soon as possible. Thirdly, reducing the source impedance imbalance can improve voltage balance. This can be achieved by improving the grounding system and ensuring that all connections are tight and secure. Also, using a dedicated neutral for each GFI protected circuit will prevent voltage imbalance from other circuits from interfering with the GFI operation. Furthermore, using GFI that are specifically designed to be immune to voltage imbalance is possible. Some GFI are designed with circuitry that minimizes their sensitivity to voltage imbalance. Considering the grounding system is vital in three-phase systems with GFI. A proper grounding system is essential for ensuring the safety and reliable operation of electrical equipment. The grounding system provides a low impedance path for fault current to flow back to the source, which helps to trip over current protective devices such as circuit breakers and fuses. In addition, the grounding system also helps to minimize voltage differences between conductive surfaces, which reduces the risk of electric shock. In three-phase systems with GFI, the grounding system plays a critical role in ensuring that the GFI operate correctly. The The GFI relies on the grounding system to provide a return path for fault current. If the grounding system is not properly installed or maintained, the GFI may not be able to detect the ground fault, which could lead to a dangerous electrical shock. To ensure that the grounding system is adequate for GFI, several steps should be taken. Firstly, ensuring that the grounding electrode system is properly installed is important. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes that are connected to the earth. The grounding electrode system should be installed in accordance with the NEC. Secondly, ensuring that the equipment grounding conductors are properly sized and installed is crucial. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. The equipment grounding conductors should be sized in accordance with the NEC and should be installed in a manner that provides a low impedance path for fault current. Thirdly, ensuring that all connections are tight and secure is vital. Loose or corroded connections can increase the impedance of the grounding system, which can reduce its effectiveness. Fourthly, regularly inspecting and testing the grounding system is essential. The grounding system should be inspected regularly to ensure that it is in good condition. The grounding system should also be tested periodically to verify that it is providing a low impedance path for fault current. When installing GFI in three-phase systems, it is important to follow the manufacturer's instructions carefully. The instructions will provide guidance on proper wiring and grounding techniques, as well as any specific considerations for three-phase applications.